Hello, it's another chance for me to meet you in person and say thank you for those of you who've been still following the content and a welcome to the new audience. Every now and then when this happens, we talk about something not on any particular math subject, but rather about mathematics, about life as a mathematician, and you may call them advice, but I don't feel myself that confident to give anyone advice on what to do, but just sharing some personal experience. Also, welcome to my office. I don't use the whiteboard that often. I'm not a fan of whiteboards. Blackboards are amazing. But then there is this beautiful view from my office of a frozen lake. So the snow you see there is actually the surface of the lake. A little bit further to the left, people actually skate or ski on the lake. Welcome to Finland, Jyväskylä to be specific. Okay, so what am I going to tell you about today is where to start research. That's a very important question that people who start in graduate school especially are struggling with. We can search about this and read about this in many places, but I have one particular practical suggestion that you may try and see for yourself. And my idea is that begin simple. Take any simple topic in mathematics and try to learn it really deeply. Learn only one thing, say from your undergraduate topics, anything you've seen in undergraduate mathematics, but the caveat is really deeply. Take one thing that probably you liked as an undergrad, some topic that kind of intrigued you, and get deeper and learn the real thing behind it. And for the shocking example I want to give you is the fundamental theorem of calculus. Some of you may have just casually accepted some version of fundamental theorem of calculus, but then there are two parts to the fundamental theorem of calculus. Number one is you start with an f. Everything will be on some closed interval. Nothing fancy. Given some f, for example, if it's continuous, then you can talk about its integral. Of course, continuity is not necessary but sufficient. Okay, so you freeze a, and then you take some x in the interval. You take fx dx, and then this defines a function because for every value of x, this is a real number. The first part of the fundamental theorem of calculus says that then this f is differentiable, and when you calculate the differential derivative at x, it's equal to f at x. Okay, that's version 1. What is version 2? Version 2 starts with the capital F. If you begin with f, any f, and it happens that derivative of f equals f of x on this interval, then integral from any x to y of f t dt in that interval. Sorry, here also I have to change this. Already you see that simple math, it's not simple because x, that wouldn't be a well-defined object anyway. So this is equal to f of y minus f of x. Already here you may think, what is the difference between these two? in part 2, you don't even know if such a function exists. You say if there is a function whose derivative is this, then this is that. And for any other f you pick, again, this is true. In number 1, you find one such function whose derivative is actually the small f. Now, this is something, of course, you've seen, you know, although you may have not noticed that these both are called fundamental theorem of calculus. Now, when I say learn something but really deeply, okay, the really deeply would be in the precision. So mathematics is all about precision, and research mathematics is nothing but precision. What is exactly required of f? What is the minimal assumption on f? We know that the integral is defined, say, for jump discontinuities. We also, if you remember, have this result that if the set of discontinuities has measure 0 is a negligible set, then the integral, the Riemann integral, is defined. So there are several questions. If under the minimal assumptions, this integral, this object here is well defined, then is this true still? And is it true at every x? What happens at the discontinuity parts? The second question is, what if we are talking about Lebesgue integral? What happens then? And is it everywhere or almost everywhere? Okay, that's a good place to start and investigate. Second question. You start with some f and it is differentiable. The claim is this. What if f, in part 2, what if f prime exists, f is differentiable almost everywhere? If it's almost everywhere, remember that to define this integral, you don't need f to be defined everywhere, but only almost everywhere. At least if this is just the big integral. So if this exists only almost everywhere, then you take derivative. You might be able to integrate that derivative. If all of this goes well, do you still have this? We've seen a counterexample before, and that's the counter function, whose derivative is actually 0 almost everywhere. So it's integrable also. It's very integrable in any sense you want. So f prime, so this is my little f. So f t dt between any x and y is 0, which is definitely not equal to f of y minus f of x, of course, unless x equals y. Because the counter function actually increases for sure. Okay, it has some constancy intervals, but even there is more shocking counterexamples. But anyway, you get my point. So my point is, you've seen some math, maybe superficially. Go back to that math and question. Question the very statement of the theorem. For example, in this one, we just casually said, okay, there's a function whose derivative is f. Take this, it's equal to... Why can you even talk about the integral of that? We have no assumption about f, little f. It's just derivative of something. Maybe it has a lot of discontinuities, nasty behavior, which doesn't even allow you to integrate. So I challenge you with this task. Write down the most precise statement, not proof, just this statement. Write the most precise statement of the fundamental theorem of calculus that you can. Just one version of them. Okay. What is my idea with this? Where am I going with this? What I claim and predict is that when you scratch deeper and when you try to understand something in its full precision, you discover a lot of math. You will branch out. You will see, for example, from this idea we came up with the counter function. Math is all connected, of course. And if you try to understand one thing really well, it naturally leads to you also learning a lot of other stuff nearby. If you find this example too simple and you're saying, okay, I'm beyond fundamental theorem of calculus, show me something better, here is another one. And this is really a challenge for everyone interested and wanting to really pick up something serious and study. So there's something called Brouwer degree or topological degree, because degree has so many meanings. If you want to go on your own and search about this, make sure you find the right notion. In its simplest case, it applies to the following. So you have some domain, connected open set, and its boundary say, well, that's actually part of boundary is what? So in the nicest case, the idea is that this boundary gets mapped to something, okay? And then to this continuous function, if there is a continuous function from the boundary into this other space, so both of them have same dimension. You go from Rn to Rn. If you have a continuous function, then to every point outside this image of the boundary, you assign a number. Okay, so you have degree of f with respect to this open set U at the value y is some number. So you define it. How you define it is part of the puzzle. With amazing properties. For example, this degree is always an integer. If you are completely away from the set, it's 0. It's locally constant. So if you are just in the same component, degree will be the same for all the points there. So it really just is not defined on y, but rather on the component. So everything in this green part will have the same degree, no matter. The other thing is that you can actually use this to also define a degree, or maybe actually in some text the definition is already for continuous functions on the set U, not just its boundary. But then the claim is that degree only depends on the values along the boundary. So if G and V are defined on closure of U, then their degrees will be equal everywhere if they agree on the boundary. And actually, more is true if f and g are just nearby to each other in supremum norm, then they become that. So there's a lot of stability. So if epsilon converge uniformly to f, then degrees converge. But because degrees are integer values, actually degrees ultimately become just the same for all of these functions at all values, and so on. And this degree is can be used to prove Brouwer fixed point theorem, because you take a map from the circle to this, you take the identity map, and then I said that if you have any other continuous function from interior to the interior, if you can extend this to the inside, the degrees must be equal. In particular, every point here will have degree 1. But to have degree 1, actually you must be in the image of the function. So there is some point definitely then that maps there. So the map is surjective. These types of arguments are used in million places, in analysis, in geometry, in manifold theory. Mentioning about manifolds, degree makes sense on manifolds. The best book to learn this from is Topology from Differentiable Viewpoint by John Milner, of the same dimension. You can also talk about separate dimensions. So my challenge for you is to find out from here and there. Maybe you can start on Wikipedia. Stack Exchange, I found a beautiful long answer to some question on degree theorem, just going through everything. Degree has connections to the vector fields. So if you have a vector field on U, some kind of index of it predicts the degree. Of course, all has to be made precise, and many more. So you have seen the degree actually before, and that is when you were talking about a winding number in complex analysis or maybe some other sources. If you've taken algebraic geometry, by the way, this degree also agrees with that degree. So there are millions of equivalent characterizations of degree with one definition. With one definition, for example, you get immediately that this is an integer. It's just from the definition. While if you use a different definition, just showing that it's an integer is a great deal. And of course, these equivalences produce very amazing results. So back to where you've seen this degree before. In complex analysis, for example, you take a curve and then you talk about its winding number around the point. This is actually degree. So winding number, you have a curve gamma from say 0, 1 into your space, R2 here in this case. How do you realize it as a degree? You can, because it's a closed curve, this is nothing other than a continuous map from the circle onto that. And now this is a map from, not from R1, but from R2 to R2, again, just defined on the boundary. And we saw that there is a degree. So try proving, so find some resource where degree is defined. Take your favorite definition of degree and your favorite definition of winding number. For example, in complex analysis, it's through line integral z minus w minus c. So this defines the degree at w. Then you also divide by 2 pi I. Also, this is some integral of the argument of the curve, how many times the person standing here rotates as they follow the particle traveling along the curve. Anyway, then this becomes a theorem. Prove that this is equal to that. And then the list goes on and on. So back to the original question, where to begin research? Begin here. Take anything and then try to really understand it well, especially pay attention to statements. Whenever you read the result, a lemma, a theorem, a corollary, always ask if it fails on stupid examples. The first thing you do is what I call, apologies, the BS check. Does that theorem even make sense? For example, we have this amazing Cauchy theorem that f of z is equal, if you have a holomorphic function, you have this z here, and there is a curve that goes around this. And imagine that this curve has winding number 1 for simplicity at z. Then the claim is that the value of f at z is some integral of over this curve of fw over probably something like z minus w dw. So line integral along the curve. When you read such a theorem, what you should really ask yourself is, wait a second. The values of it on this side, only values of f along this curve are considered. And how could they uniquely decide what f is going to be at the point z? How could values far away from z, and arbitrarily far away, you can take this loop 1,000,000 miles far away from z, and still the result is true. How on earth could that be true? Once you ask yourself that question, once you do that BS check, and then you check the proof for stuff, then you realize it is true, and then you realize how deep and how strong this result is. This is saying that if you have f and g, and they have the same value along this curve, then they will have the same value in the interior of the curve. And that's again true, and that's an amazing property of holomorphic functions. But the way to appreciate this is to by just reading this statement and asking yourself questions. If f is 0 along the curve, then f is 0 in the inside. Just an amazing truth about holomorphic functions. To convince you, as a last example of why you should be thinking in these terms and why even prominent mathematicians do that, let's look at this example on Math Overflow. Does the inverse function theorem hold for everywhere differentiable maps? First of all, the statement, the question, what do you mean the inverse function? I mean, calculus, right? Multivariable calculus. What is this doing on Math Overflow? And not even Math Statistics yet. The point here is that they don't assume continuity of the derivative. Remember, every usual calculus textbook you open, the inverse function theorem is for C1 functions. You need the continuity of derivative. And then there are counterexamples just already in R1 with a point with lots of oscillations so that locally the function is never injective. Guess who has answered this question on such maybe topic that everyone knows? Terence Tao, the most prominent mathematician probably alive today. If Terence Tao takes the time to not just brush aside something about inverse function theorem, why should you? And look how engaged he's become with this. Actually, he's written up a full note on his web page based on this conversation here. He's collected basically things that are told here into some nice argument. They find someone has found a paper answering the question in the post, and then it's in Russian. So Terence Tao jokingly says, "Thanks, David. Now I just need a physical copy of the paper and learn some Russian." So he means it. Then following that, 15 minutes later, you can see, he says, "Oh, there's a translated copy at American Mathematical Society Translations, volume this. I still need to get to the library though." He follows on this. You may think, wow, what is Terence Tao doing? How does he do research? Nothing crazy. Believe me, I'm not a great mathematician, but I've worked with great mathematicians. Piotr Hajwasz, Pekka Koskela, they always begin with the simplest ones. When there is a question, is every metric space blah, 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 blah this? Well, let's try line segment. If that doesn't work, let's check union of line segment. Let's check a counter set. Let's check dimension 1. If that doesn't work, then dimension 2. They don't start top to bottom, they start bottom to top. They start with the simplest examples. And that I have seen in all great mathematicians, that they take everything theory seriously. And for example, with Piotr Hajwasz, every time he teaches an undergraduate course, he writes fresh notes. He's not like, this is stuff I know by heart, so let me just produce something. They care about stuff, and they don't pass any mathematics as cheap or light or too easy. So that, ladies and gentlemen, is my advice for you. If you want to really begin research level mathematics, pick your favorite topic, try to learn it, but to the fullest satisfaction of your heart. Leave nothing for doubt. It's for you and no one else. You don't want to convince someone something is true or false. You want to see it. You want to visualize it, whatever, so that you know what you're talking about. That's the thing. Be honest to yourself and learn stuff deep. Just in case you wonder, I for one, I'm very interested in finding a neat proof of this last part, that the degree defined via this is actually the winding number. The thing about this that is intriguing is that the winding number is by definition for piecewise smooth curves, because you want to define the integral. But remember, we said degree is defined for continuous curves. So there also comes some subtleties. But anyway, what is your favorite mathematics from your undergrad that you wish you really understood well? Put that in the comments, maybe. That way you inspire someone else to pick up on that. And also share your opinion about this. Do you have other suggestions? Do you have variations of this method that I told you that you think can work even more efficiently? But whatever it is, learn one thing, but learn it deeply. Until next video, which will be about projections of sets again in the plane. Have a great one, and thanks for watching.